I know why already. I'll show you, I'll explain to you why later on. So, I know why. Because I recorded in 4K. Oh. That's why. That's why. Okay. That's why, yeah. Because 4K versus the normal HD even, you're talking about 8 times? Yeah, a lot more, yes, correct. Anyway, coming back to this. So the idea over here is that you'll be, okay, why this is so. So the path difference over here is equals to 0, exactly, 0. So if the path difference is 0, it means that it should satisfy n lambda. Right? It should satisfy this condition because n is 0. However, if this gives you minimum, it means that it is not this kind of scenario where we derive this based on the assumption that the sources are in phase. Because this is only true, this leads to constructive interference assuming the sources are in phase. Agree? So therefore, if it is this condition yet it gives a destructive interference, it means that it must be out of phase. Okay? Important idea. Cool? So first thing that you should look out for is what's the sound that you hear in the center, or is it a dark patch or bright patch? If it is a bright patch, everything is safe, it's the normal condition. If it is a dark patch or a soft sound or no sound, then it is you must swap around. Cool? Okay? Point number 2. This is a very important idea I'm going to develop. You're going to hear me using the word important again and again because it is really important. Let's consider this point. Let's consider when the sources are in phase and when the sources are out of phase. Now, can you see that at point x, where path difference at x is equals to lambda, path difference at y equals to half lambda. So this is x, this is y. Now, if the sources are in phase, over here, at point x, is it constructive or destructive? Constructive, exactly. So you hear a loud, and at y you hear soft or no sound. Agree? I'll explain why soft later on. Now, over here, if the sources are out of phase, at point x, what do you hear? Soft or no sound, yeah? And then for the x, you'll be loud. Now, think about this. 180 degrees. That means they are half a wave out. When one is positive maximum, the other one is minimum negative. Half a wave out. Yes, correct. It's the same. Half a wave and 180 degrees and pi radians out of phase, they're all the same. Okay?
So here we are specifically talking about out of phase by
half a wavelength. Yes, correct.
What if it's not half a wavelength?
Yeah.
But
what if it is? Okay, what's your question?
But the definition of out of phase itself, it's just half a wavelength difference?
Yeah, correct. No, half a wavelength for your syllabus. Half a wavelength or pi or 180 degrees. How about if it is in between? The good news is that it's not in your syllabus. Yeah, the good news is it's not in your syllabus. Sorry? No, it will not create a mess. It will just be you have to tweak the equation a little bit further. It's a little bit more complicated mathematically.
But the result you see
that's correct. You still have bright dark, or loud soft, loud soft. If you have a phase difference which is somewhere in between 0 and 180 degrees, then the O over here will be neither loud or soft. In between, yeah, correct. Yes, correct. But your syllabus, very clear cut, is either in phase or out of phase. Cool? So let's take a look at this. Now, imagine the case. This is important. Imagine the scenario where the sources changes phase at 1 million times a second. What will you hear at these 2 points? Loud, soft, loud, soft, loud, soft, 1 million times a second. So are you going to hear the loud, soft varying 1 million times a second?
You're going to hear like in between.
Exactly. You're going to hear in between. So you're going to hear somewhere in between. You're going to hear somewhere in between. So as you walk past from here to here, are you going to hear loud, soft, loud, soft, loud, soft? You're not. So therefore, it is a very important condition for the sources to have constant phase difference. It need not be in phase. Be very careful. It need not be in phase. It need not be out of phase. But if it is in phase, it has to be always in phase. So you only see this part. It cannot be in phase, out of phase, in phase, out of phase, in phase, out of phase, like 1 million times a second. You're not going to hear any loud or soft. You're just going to hear somewhere in between. You get it? So this condition is what we call coherence.
So it's to do with the source of the wave.
Okay.
You try to force it.
It's a very good question actually you have over there. When is a scenario where the phase changes? Let's see, for example, if you have light from a bulb and then you have this. Can you see light from the bulb comes from different point on the filament? Yep. And how does the lamp produce light? The lamp produces light by having electrons colliding with the atoms, which is a random process, random place, random time. So the light reaching here will be reaching these two slits from different places of the lamp produced at different time. So the phase difference between the light reaching there will be totally in a mess. Yeah, it will be a total mess. So in this case, that's why when you have two slits held against this kind of lamp, you'll never see a pattern. You need a laser, which is a coherent source. Yeah. So it is very easy to get incoherent sources, which is just a lamp. Ken? It doesn't matter whether you use DC or AC because the mechanism of light production over here is basically random. Yes, correct. It's random. Yeah. So this is the first condition for observable pattern. Cool? Must remember this condition for observable pattern. Condition number 2. If you see, can you just go to the notes and if you see the word coherent, can you just, put lots of love around it and lots of stars around it? It's really important. This is the kind of thing you must remember, kind. Yeah. Source 1, source 2. A weird what?
One random question. Does it have anything to do with polarization?
I'll come to that later on.
Okay.
Yeah, there is. Okay, let's take a look. What happens if the amplitude of the sources are not the same? If the sources have the same amplitude, you have a huge amplitude over here for constructive and zero amplitude for destructive. So what you're going to see over here is that you're going to see bright and then very dark, and then bright, very dark, bright, very dark. So very distinct pattern. Now what happens is that if you have sources not having the same amplitude, constructive, a slightly smaller amplitude, but this may sound a little bit philosophical, but the reason why you see a bright patch is because of the dark patch.
Yeah, comparison.
If everything is bright, then there's no bright patch per se. Yeah, so the reason why you see this is actually because you have a dark patch. But take a look at this. If you have this trying to cancel out with that, can it cancel out? No. It can't. Not completely exactly. So there will still be some light at the dark patch. So what happened is that the contrast is reduced. And can you see that if this gets even smaller, the difference between this and this will get even smaller, up to the point where you cannot tell the difference. So therefore, to have observable pattern, you need the sources to have similar amplitude. Yes, correct. Similar. That's why similar can really. So that's condition number 2. Amplitude must be similar. Cool? Yep.
What is the wavelength? Is it exactly half or 1?
What if the wavelength is exactly?
I mean, the difference in.
Which is what I mentioned just now. If the wavelength, which is not in syllabus, yeah. It changes the equation slightly. Yeah.
They overlap. If it's 0.2, then 5 times 5.
Have some patience. I'm going to show you at the end of this, if I have time, I'm going to show you a method to derive the full mathematical expression, regardless of what's the phase angle. Yeah, it will reduce to 0 degrees in phase. It will reduce to 180 degrees out of phase. It will reduce to anything in between you want. Yeah. So just give me a little bit of patience. Yeah, a little bit of patience. I'll show you. Cool. So condition number 2. Amplitude must be similar. Need not be the same, similar can already.
When we learn the equation, can we use it in exam?
Cannot. It's
because the light one was accepted.
IB examiners will not be accepting.
Please.
Yeah, unfortunately. I mean, yeah. Okay, the next one. The third condition, is it still recording?
Yes, it is.
Okay, third condition. The light must be unpolarized or polarized in the same plane. Yes, correct. It is very common sense. Let me explain to you why. Remember the idea that you only see bright patches because of the dark patches.
Yes.
So in order to see a pattern, you need destructive interference.
Yes.
Agree? You need dark.
If they're not in the same plane, then you cannot.
Exactly. How is the light oscillating in this way, cancelling the light this way? Just not possible. This and this just doesn't cancel, right? You need to be in the same plane so that you can cancel out. So that's it. But why is it that unpolarized can work? Because for unpolarized light, for every axis you have another corresponding axis, exactly. So this is simple. Okay?
So what about constructive interference?
What about constructive interference? What about?
Like if they are polarized, then the
At 90 degrees, you mean?
yeah.
Let's see what happens when you have light polarized at 90 degrees. Let's see what happens when you have the same plane. So when you have constructive interference, the electric field points in the same direction. This is constructive. So you get a longer arrow. And when you have destructive, the light electric field is pointing in the opposite direction, so you have nothing. When you have light pointing at 90 degrees, this is what happens. Your so-called constructive is going to give you this. Your so-called destructive is going to give you this. So there's no difference. The electric field is as strong.
It's just direction change.
Intensity-wise, is exactly the same. Yeah. Exactly the same. You see, if this is E, this is E, this will be root 2E. This will be root 2E as well. No diff.
Amplitude changes.
Amplitude,
The
don't.
square root.
Yeah, when you square this and square this, it's the same intensity.
1 plus 1 equals 2.
Your eye don't tell the axis of polarization. Your eye only tell the intensity.
So
Can?
why do they need to be in the same plane?
Which is exactly what I mentioned. It's same plane so that you can cancel out. If you're not in the same plane, like 90 degrees, there's no way you can cancel out this one using this one.
I think it's just.
And remember the concept is that in order to see a pattern, you need the dark spots. You need the dark spots. So you have to thank the dark spots for the bright spots to be seen. A little bit spiritual, but sometimes you only know what is good when you see what is evil.